Go. I mean, not coughing. Go for doing this. Hello and welcome back to Calculus1 with my radio voice. I don't know. Do I sound different? I sound different. Yeah, I finally hit puberty, so all right. I have deeper voice now. So min max, called extreme value. Chapter 4 is on application of derivatives. Yes, we did have a word problem 311. I always argue 311 should be in this chapter because it's all about application of derivatives. Entire chapter 4, we are going to apply derivatives to different concepts, which include analyzing function in terms of min, max, increase, decrease, concavity. We're going to learn to graph difficult composite functions by hand by utilizing derivatives. We're going to learn optimization, which actually can land you careers. Linearization for to compute some of the difficult stuff. And the very last section of chapter 4 will introduce you to antiderivatives, also known as integrals, which will transition us into chapter 5, which would be all on integration, and we will close out Calc 1. So tonight we are starting with learning about the concept of extreme values, which would be minimum and maximum of a function. So if we draw a curve f of x, we will be able to pick there we go, a point where the graph would have a horizontal tangency with a slope 0, and we might be also able to find another one with horizontal tangency where slope is equal to 0. So these values would be called extreme values. This one would be some form of maximum point, and the other one would be some form of minimum point. There are different kinds, so we have to be careful about that. So now, when we understand the max and the min and what they have, which is horizontal tangency, we can start categorizing these. So I'm going to draw another one. Oops. Note that the second peak is lower. Yeah, now this is my f of x. So we are going to have a horizontal tangency over here, horizontal tangency here, and horizontal tangency here. They all have slope of 0, which means they are producing these extreme values. Now, both of these on top are max values, but they are different max values. The one on top is called absolute max, also known as global, depending on which literature you read. Some calculus textbook will call it absolute, and some will call global. And then the other one is going to be relative max, also known as local. Please observe that for absolute maximum, there are no points on the curve that are higher than the y value of absolute max. Y value of absolute max is the highest point of the function over entire domain. So that's the absolute max. Why is the other one relative max? Well, easier to understand, local max. The other max is the boss in its surroundings, right there. Because I can pick a point right here, and that point has a higher y value than my maximum over here. So we call it a local max because in the neighborhood of that max, it is the highest point. But it is not the highest point of the entire function. Therefore, we differentiate between the local max or the relative max and the absolute global max. You don't have to use both words. You say one or the other word, and I will understand, right, whichever word you use. Now the question is, what is this minimum? Is it absolute minimum or a relative minimum, local minimum? Relative or local, very good. And the reason is, all of these points here and all of these points here have a lower y value than a minimum. Therefore, that minimum cannot be a global minimum because there are lower points than the y value of the minimum, so it must be relative or local. So do we all understand the difference between relative minimum and absolute minimum? Relative maximum and absolute maximum? So if you have the absolute or the global, right, wording, that means that is absolutely highest or the lowest point of the entire function. So now if we go back to our, let's say, x cubed version of the graph, those min and max are what? Local or global? Local, very good. Because local min, because all of these values are lower than our min, so that makes it, right? And then you have the other edge that goes forever up, and that's going to make this max also to be local or relative. So once we understand these concepts and understand which word is appropriate to use with each of these cases, we move on to the way to calculate this. We've seen that each one of these has a horizontal tangency with a slope being 0, which means if slope is 0, what else is 0? The derivative is 0. Yes, the derivative is 0. So that will be our ticket to find these values. Derivative equal to 0. Now, this is where your ability to factor and simplify expressions after taking the derivative are going to kick in full force, right? Which is why I bugged you so much to get that into your system. And every time you take the derivative, you simplify. Now, before we do those calculations, let's write some stuff in red. Definition for a critical point. Critical point of a function is a point in the domain where number 1, the derivative is equal to 0, the derivative at the point is equal to 0, number 2, or number 2, the derivative at the point does not exist. So that will be our critical point. Critical point can be minimum, critical point can be maximum. And it also could be something else called inflection point that will reveal itself next week. We don't deal with that today. So once you have a function, you will take the derivative, you will set the derivative equal to 0, you will have equation, and you will calculate the x value at which you have min or a max, and then you just have to figure out, is that a min or a max? So let's practice this on a function that we all know, y equals x squared. Can you tell me if this function has a min or a max, and where? It has what?
Absolute minimum.
Absolute minimum. Keep talking.
At 0.
At 0, 0. Very good. So we already know the answer. Let's see if the calculus is going to just verify that answer. So I'll just put here in orange. We know 0, 0, ABS min. We already know the answer. We can also draw the graph and verify that, right? But let's use calculus. In calculus we said that we are going to take the derivative. You can do, if you want y prime is 2x, and here is the $1 million step equal to 0. So by equaling the derivative to 0, we are forcing the x values that will give us horizontal tangency, right? Remember that this is a function which generates all slopes, and the only slope I want to generate is the 0 slope, which is horizontal slope, which means the tangent line there will have a max or a min. Solving this equation, x is equal to 0. When you only have an x, it's not a point, it's a coordinate, it's a number, because x line has values as a number line. So 0 is a location on the x number line. That's the reason why this is not called critical point, it's called critical number. And then when you calculate the y value for it, it becomes critical point x comma y. I understand it's a little bit picky, but it's math, so what do you expect? So the wording is, this over here is critical number. Now you take your critical number and you calculate your function at critical number to get the y value. So that's your y. And now you have 0, 0, and that thing is called critical point. Right? So x value alone is called critical number. When you add y to it, it becomes xy. Now it's a point, right? Because it's ordered pair. Now, as we discussed above, in purple, the max and the min. It can be max, it can be min, or this third mysterious thing that will be revealed next week. So I don't have any tools yet from calculus to determine whether 0, 0 is a min or a max. So the hack way to do this would be to compute the y values to the left and to the right, and then just use common sense. Because if the y values to the left and to the right of 0 are above 0, then this point is below, meaning it's a minimum. If the values x and y are above, because you are either going to encounter this situation or you're going to encounter this situation. Your critical number, critical point, is always min or a max. So the 2 points that you calculate to the left and to the right, they are either both above or both below. Now, the homework might have problems to trick you and make you think about this mysterious third case that we are not discovering yet, and that is situation when one ends up being below and one ends up being above, right? Is this point min or a max? No, it's neither, right? Now, what kind of graph has the squiggle like this? X cubed. Now, if you take a look, when you have x cubed function, when you differentiate, you get 3x squared. When you set that puppy equal to 0, what do you get? You get your critical point to be 0, 0, right? So, but we know that 0, 0 is not going to be min or a max. So we have to be careful. So now that third case is coming up next week. So what we have now is, since we don't have the knowledge of the first derivative test yet, we are just going to use middle school method. So to discover what this is, I'm going to calculate function at -1, and I'm going to calculate function at 1. So -1 squared is 1, and 1 squared is 1. So I have the situation where this is my 0, 0, this is my 1, 1, and this is my -1, 1. So clearly, it's a minimum. All you need to do is to compute to the left and to the right from the point that you found as a critical point. Now, y equals e to the x. Do we have a min or a max? No. We don't have either one of those. Your e to the x function, there we go, is asymptotically approaching x-axis. Therefore, it will never have a minimum value because it will never hit x-axis. It will never stop. It goes to 0 in negative infinity. The right-hand side is rising forever. So we do not have min and max on e to the x graph at all. Can we detect that using calculus? Well, of course. Y prime is e to the x, and now we set that equal to 0. E to the x equals 0 has no solution. Now, before you start screaming why and how, e to the x equals 0, ln both sides. What do you get? You get x equals ln of 0, which is negative infinity. Right? So no solution. And we did not come up with any points that would be candidates for min or a max. Therefore, e to the x does not have min or a max. Calculus said so, right? So we move along to the next example. How about sine x for all of you in love with trig? Y equals sine x. Do we have any min or a max? Yeah, we do. How many? Infinitely many. And they are all what? They're all the same. They're all one, and they're all absolute. All of them are absolute, yeah. They're the same. How about minimum values? Same thing except at -1. we have infinitely many. You have a wave that goes on forever both ways. Infinitely many absolute max values at 1. Remember, no other point is ever higher than 1 on the entire domain of sine. No other point is ever lower than -1 on the entire domain of sine. Therefore, we have infinitely many absolute max and infinitely many absolute min values.
So it's okay to have multiple absolute?
Yes, just like in statistics you have multiple modes for, right? You have a bimodal graph, so you go to a parking lot, you do assessment of all the car colors, you came up with 8 black cars and 8 red cars and everything else had less than. For a qualitative variable, that would be, so you would have 2 modes. So now we can have that in calculus as well. Now, what is my derivative? Very good. We set that equal to 0. When is cosine x equal to 0?
Zero.
So we're going to take it outside, or because I heard 3 answers that are all different, right?
0 and
Should we take a vote now? I mean,
0.
are you right?
Yeah, it's pi over 2 and 3 pi over 2, right?
Yeah.
The range of 2 pi. Oh,
So, don't call my name in vain. Hold on. I'll do it. I'll do it over here. So, I'm solving cosine of x equals to 0. You know what? I'm just going to leave this space to finish this problem, and I'm going to teach something about solving equations. All right? And I will come back to this problem. Deal? Ready? X plus 2 equals to 5. Why are you laughing? The inside of this will solve all of your issues with equations forever. So, what is the noob way to do this? Subtract 2, exactly. Right? So let's not do that. Let's solve this the cool way. What you have on the left is a function, x plus 2, which you can graph. What you have on the right is another function, which is constant function, which is 5. If you graph the left-hand side and the right-hand side on the same coordinate plane, the intersection is the solution. Did you guys solve 2 equations with 2 unknowns by intersecting them in Algebra 1? Yeah, you did. System of equations, right? If you look at the corner of the classroom, it's the intersection between 3 planes called the wall, and the ceiling. And they intersect at the point in the corner, right, where the spider sits. So, or the security camera. It's one or the other. Or both. So, to solve this equation, all I need to do is to draw these 2 functions on the same xy plane. So, y-intercept is 2, and I draw 45-degree line, and then I go to 3, 4, 5, and I draw horizontal constant function 5. Where are they intersecting? What is the intersection here? X equals 3. Intersection is at 3, 5. X equals 3 is the solution of this thing. Now, this goes for every equation under the sun. Can you solve every equation by subtracting 2, multiplying by a half, and can every equation be solved that way? The answer is no. Let's take a look at this equation. X plus 2 is equal to ln x. If you have rage issues, please try not to break anything at this point. What is the way to solve logarithmic equations? Well, you get rid of log by exponentiating both sides. And the log will expose the x, right? Woohoo! So you exponentiate both sides, e kills the ln, and now you have that x equals to e to the x plus 2. So you freed this x here, but then you buried the other one. There is no mathematical witchcraft that you can perform here to solve this algebraically, because you have a polynomial function equaling transcendental function. They are not in the same realm. So as you free up one side and create a single x, you bury the other side under the function. You can try this with x and sine x. And as soon as you free up x on one side, the other side gets buried under the inverse sine. These equations cannot be solved. So how do I solve this? I get to graph them. If they intersect, the intersection, the x values of each point of intersection, is going to be your solution. So I should have gone with x minus 2, so they can intersect. I changed the problem. So now I have x minus 2, that is a 45-degree line going through negative 2, and then I have ln x. This equation will have two solutions. I don't know what they are, but I know it has two solutions. We can find them, obviously, numerically. So the only way to solve 100% of equations in life is going to be graph the left side, graph the right side. If the two graphs intersect, x values of that intersection point is going to be the solution. If the graphs do not intersect at all, there is no solution. I go back to my e to the x now, and I show you the equation here. And in this equation, the left-hand graph is the e to the x graph. The right-hand side is the x-axis. Didn't I say that they will never intersect? If they never intersect, what they don't have?
No solution.
No solution. They don't have a solution. So no solution in that case. Now that brings us to any trig equation. What do I have? I have a cosine graph which starts at 1, goes down, goes up, goes down, goes up, goes down, goes up, forever. So I have my cosine x graph, and in blue I have my 0 graph. Where do they intersect? They intersect at every purple point. Here, 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 all of which are solutions. Now this one happens at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2. On the other side, I have negative pi over 2. So all of these are happening at x equals pi over 2, and then I need to add a pi to it, so plus n pi. For n, which is I for n, that is equal to plus minus 0, 1, 2, 3, 4, forever. So let's test this. So my pi over 2 is the first solution that I see, and my n is equal to 0. 0 times pi is 0. Pi over 2 plus 0 is pi over 2. So that's my first dot. When my n is equal to positive 1, pi over 2 plus 1 times pi is pi. Pi over 2 plus pi. Pi is going to be 2 pi over 2, the common denominator. 2 pi plus 1 pi is 3 pi over 2. 3 pi over 2 is the next one. When it's 2, you get 4 pi over 2 plus 1 is 5 pi over 2. 7, 9, 11, and so on. For the minus side, the same thing, you just have negative and 1, negative 2, negative 3, negative 4. So, I am able to obtain all, this is infinitely many critical points. And each critical point sits at pi over 2 plus or minus n pi. Now, you know that for sine, your first peak, which is maximum, is where? At pi over 2. And then the negative one is at 3 pi over 2. And then the next one up is 5 pi over 2. Now if you go back all the way months ago, we talked in chapter 3, section 2, graph the derivative graph, looking at the function. Anytime you have a mixed or min or a max, you put a dot on the x-axis, right? Anytime you have max or a min, you get to put a dot on the x-axis. Then, if your function is increasing, the derivative is positive. If the function is decreasing, the derivative is negative. If the function is increasing, the derivative is positive. Right? It all has to click because it's math. No exceptions. Right? So all of these are critical numbers. And now that I have critical numbers, I can go one by one and determine which ones are max and which one are min, calculating their y values, right? So pi over 2 into sine, you get 1. So all of these max values, all of these min values, and there are infinitely many of those. Now to go back to this talk on solving equations, 2 cosine x minus 1 equals 0. Well, you use algebra and rewrite this as cosine x equals a half. And then forget about unit circle, forget about all of these things. We have our cosine graph at 1. This is where the 2 pi is. In the middle is a pi. And what do I have? I have a half. So here they are. So where are my positive values? My positive values of cosine when it's equal to a half are pi over 3 and this one. What is that one? 4 pi over 3. Or 5 pi over 3. Four or 5? Or 4? Or should be 5? It has to be symmetric. So if there is a...
Symmetric relative to your pi.
Oh, yes. So it has to be 5, right? because the 2 pi is going to be 6 pi over 3. So if you have a pi over 3 separation here, you must have pi over 3 separation here, because it's symmetric on either end. So you can use graphing method to determine the number of solutions. Now, unfortunately, no one teaches that anymore, so it's kind of tough to realize that. Let's see some examples in a textbook. Yeah.
I would imagine that if you're still having trouble with figuring out that second piece of it, you could just take the first piece and subtract it from 2 pi to get the second piece, right?
Yes. For cosine, not for sine. All right, so find the critical points. All right. Let's start with the vanilla exercise. 24. CP, critical points of f of x equals 1 over 8x cubed minus 1/2 x. What are you supposed to do to find critical points? Good, go. Okay, so we know the rule. Take the derivative and have your 3/8 x squared minus 1/2, and that's equal to 0. To solve this equation, multiply everywhere by 8, just to make it easier. We have 3x squared minus 4 equal to 0. And then x squared is equal to 4/3. Take the square root of both sides. X equal to plus minus 2√3/3. When you rationalize, I skip 7 steps. So now, these are your critical numbers. You have 2 of them. And now you take each one of these into original function and calculate y values. So y is equal to f of 2√3/3, which is 1/8, 2√3/3 cubed, minus 1/2 2√3/3. So this is equal to 1/8. 8 times 3√3/27 minus 2 and 2 cancels. You just get √3/3. Now 8 and 8 cancels, and 3 and 27 cancels to get a 9. Over here times 3 to get a common denominator. So I have 1√3 minus 3√3 is minus 2√3s divided by 9. So the first critical point is going to be 2√3/3 and negative 2√3/3. Now for the second one, which is negative, and these are odd exponents, all the calculations stay the same. Yeah, just make exactly. So the first number would be a negative 1/8 2√3/3 cubed, and then minus minus is plus 1/2 2√3/3. So it's going to be 2√3/9. Right, they swap. So now I have negative 2√3/3 and 2√3/3. So this will be your max, and this will be your min. Now, how do I know that? Original function is a polynomial. Yes.
I think the y values are not right on the max.
Think they're swapped?
They're 9 denominator. Otherwise, they're didn't you find that the y values were negative 2?
Oh, you mean I copied wrong. Okay, thank you. Thank you. Okay. No, I was just wondering if you're paying attention, and you clearly are. So that's it was just a test. When I do these things, my brain is already, in the next concept, so I was not paying attention whatsoever, which I should. All right, time for. So, I just wrote the max, and I did not calculate the points to the left, to the right. I just knew. How did I know?
Because
Yes.
one is positive and one is negative.
Okay, that has to do with it. Yes.
I'm sorry, the y values are pretty good. So the
Y values, yes.
Yeah.
So she said one is positive, one is negative.
Yeah.
It has to do with that. We have a polynomial. Polynomial is continuous, it's not interrupted in any way. So if you have a positive value and a negative value, right, if you play a little bit with graphs, it's difficult to draw. So cubic graphs, they go like that, go like this. And clearly, always the one that has a higher value on y is a max, and the one with the lower value on y is a min between the two when you look at them, right? Are completely different than when you have a vertical asymptote, because the vertical asymptote can trick you. You see, you can have a minimum on the higher y value and the maximum on the lower. So you can use, so this functional analysis is coming up, but you can always use point to the left and point to the right just to be safe. But for polynomials, when you have polynomials which never have any vertical asymptotes, you guys are always safe to assume that the larger y value will produce maximum and the lower will produce minimum. But that works only for polynomial, right? Now, no one asked yet because you probably missed it. Remember this one? Critical points also occur when derivative doesn't exist. And those cases pop up here and there. The most famous case of all is y equal absolute x. What is this?
It's a V.
That's a v. It's a corner. So it's not differentiable at that spike at x equals 0. If you take a look at the derivative from the left is trying to be -1, the derivative from the right is trying to be +1. Well, you can't be -1 and +1 at the same time, right? The bank account is either in a minus or a plus, can't be in both. So, at this case, y prime at 0 does not exist. But we still have 0, 0 to be absolute min. So this is an example where you have the absolute value doesn't exist, the derivative doesn't exist, and the point is actually 0. Sorry, minimum. There are other examples that you guys are going to run into in a book. Clearly, if you have a vertical asymptote running to that point, you can't have a point along the vertical asymptote, right? So it would be really silly, for the lack of the worst word, to try and calculate minimum or a maximum for 1 over x at 0. Because 1 over x has a vertical asymptote at 0. And what we know about vertical asymptotes is that they cannot have points along vertical asymptote because nothing punches through vertical asymptote. So if you don't have a point, well, you can't have a critical point, right? Because you just can't have any point. And critical point is a point. So you will never find min and max along vertical asymptotes. If you need to write that down, you can. But it should be common sense that if you are not allowed to have any point ever on a vertical asymptote, then you clearly can't have critical point on the vertical asymptote either. Because critical point is a point. Before anything else, it's a point. So now we understand that to find min and max of a function, we simply find the derivative. If the derivative doesn't exist at a point, you check if it's a vertical asymptote. If it's not a vertical asymptote, then you might have min and max. If you are able to find the derivative and set it equal to 0, solving equation will give you location of the critical number, which turns into critical point, which turns to min or a max. All right, we still have another problem to try, and then we will move to the last concept in this lecture and then the break. So one more. How about f of x is equal to x minus 5 inverse tangent of x? Yes, I carefully picked this one. No, just take the derivative. If you don't know what it is, look up the formula. This is the one that you absolutely have.
But okay, yeah, I was right. So so is the derivative for the inverse the same as the derivative for the normal one?
Nope. 3.10 in the book.
Oh my god, I totally forgot about that.
Yeah. Okay, so the derivative is 1 minus 5 divided by 1 plus x squared. We said this equal to 0. So 5 over 1 plus x squared is equal to 1. Cross multiply 5.
Negative 1 and
1.
Oh, just switch it, sorry.
Yeah. I switch the other side and then switch the sides. 5 is equal to 1 plus x squared. And now x squared is equal to negative 4. If x squared is equal to negative 4, your solutions are complex. So no real solution, which implies no critical number, which implies no critical points, which implies no min-max. It's just a train of thought.
I don't understand why multiply by negative 1 though.
What do you mean multiply by negative 1?
How did you get negative 4?
Yeah.
Shouldn't it be 4?
It would be x squared is equal to 4, right?
I was just testing you. All right, good. So x equals plus minus 2. X equals plus minus 2. Good. So those are your critical numbers. Now we need f of 2. F of 2 is going to be 2 minus 5 tangent inverse of 2. Use abacus for that. Make sure let's calculate. Make sure you're in radian mode on the calculator, otherwise the whole thing explodes. 2 minus 5 inverse tangent of 2 is negative 3.54. And f of negative 2 is going to be negative 2 minus 5 inverse tangent of negative 2. Well, that's just going to turn it out into positive. So negative 2 plus tangent inverse of 2. No, of 5 tangent inverse. Negative 2 plus 5 tangent inverse. So tangent 2, and you get positive 3.54. So I have two values, and tangent inverse is continuous as well, no asymptotes, so higher value is a max. We have a 2, negative 3.54 as a min, and negative 2, 3.54 as a max. Now clearly, let's say you care, right? Hypothetical. We go immediately to Desmos and graph this just to make sure that it works. So we graph x minus 5 tangent inverse of x. There it is. So we see that at negative 2, you can clearly see over here. At negative 2, you see a maximum. And at positive 2, You see a minimum. You can verify all of these calculations just by simply graphing and just looking at the piece of either graph, because you should be able to spot min and max. The last concept of this lecture is the min and max on the line segment. So if you have restricted domain, so min and max on closed interval. Closed interval A, B. So if you have a function that is restricted on a closed interval, you must have absolute min or absolute max. If you go and say e to y equal e to dx, which does not have min or max, if you go and you say e to dx on 0 to 1, you immediately created min and max, because your function that used to be this now starts here and ends there.
We're still on Desmos.
Yeah.
Sorry. So min max on closed intervals. So y equal e to dx has no min, has no max. We did that problem earlier in a class. But as soon as I restrict that one to 0 to 1, and I throw away the rest of the function, I have the beginning and I have the end of the function at a and b, and those points immediately become min or max. Or you might have min and a max inside, right? So now I have a min, which is the absolute min, and I have the absolute max on a function that before did not have anything. Take y equals x squared on -1 to 3. Well, if you graph that, you're going to get this. Like a check symbol, right? For correct. From -1 to +3. Do we have our ABS max? Sure. What is this one? Local what?
Max.
Yes. Local max. Very good. And what's the one on the bottom?
Absolute min.
Absolute min. So you are not guaranteed your endpoints to be absolute min or a max or whatever. Absolute min and max could be also inside of the function. So now you have additional headache. If you have closed interval, you also have to compute the endpoints and bring that into the mix with the rest. Now the greatest thing here is that highest of all y values is absolute max, lowest of all y values is absolute min. And that's something that it's great, right? Because you're doing calculation and you have no clue what's min, what's max. But on the closed interval, right, the lowest one of them is guaranteed to be absolute min, and the highest one is guaranteed. So let's take a look at the problem from homework, and we're done. What was your favorite? Was it LN or a trig? Trig was your favorite, right? Good. So problem 63 says figure out absolute min, absolute max. F of x equals secant x on negative pi over 4 to positive pi over 4. Let me just write in blood so no one is, so you guys are not confused. This over here is called the interval. And interval has x1, x2. They're both x values. When I say I'll see you sometimes, right? Between 5:30 and 6:30. Those are both units of time. So it's the interval, like a time interval. But this is the distance interval, right? I'll see you somewhere on the street between these two stores. Right, fine. So location. All right, the derivative, set it equal to 0. You do the entire problem from before, and now in addition to it, you have to calculate endpoints. With smart. Well, it's important, right?
Hmm?
It's important.
It is.
All right. The derivative is tangent x. Good. Now we set that equal to 0. Secant is 1 over cosine x. Tangent is sine x over cosine x equal to 0. So when you cross multiply, you just get sine x equal to 0. So x is equal to 0. So we can just say n pi infinitely many. But then, do we need infinitely many of them? No, because we are on a closed interval. So we get to keep only one. Which one? 0, 1. Very good. So we get to keep only this one because of negative pi over 4 and pi over 4. The next one is pi, so that's outside of the range. The one before is negative pi, also outside of this range. So we are only focusing on x equals 0. Great. What is secant of 0? Perfect. It's 1. Yes. So now we have y, which is f of 0. That's secant of 0. Secant is 1 over cosine of 0. So it's 1 over 1, which is 1. So we have our critical point 0, 1. Now what? Now we calculate the endpoints. So the y is going to be f of negative pi over 4, which is secant of negative pi over 4. Secant is 1 over cosine, so 1 over cosine of negative pi over 4. Now, it's even function, so it's 1 over cosine of pi over 4, just minus just dies. And I have cosine of pi over 4 is very good, 2 over 2. So it's 2 over root 2 multiplied by root 2 to rationalize. So what do we get? 2 root 2 over 2, which is just root 2, right? So we have negative pi over 4 and root 2. And I have another one to be exactly the same because it's even function. Is also root 2. So I have positive pi over 4 and root 2. I have 3 points.
Did you say whether the critical point was the minimum and maximum?
Mm-hmm. So which one is absolutely lowest point here?
The critical point.
We don't have any negatives.
1.
This is the lowest, right?
Yeah.
And these two? Oops. Those would be the max values because they're taller. And this is a min value because it's lower. Great. Yay. So calculate the endpoints as well. The highest y value, maximum values, the lowest are min. All right, time for a break. When we come back, it's should be mean value theorem. Bye.